Today we're going to give a little bit of an overview of orbits, low Earth orbits, and various other topics such as the inverse square law. Are you ready to jump in? Come join us! First of all, there are a lot of questions about what is an orbit. An orbit is essentially a stable motion around an object where the angular momentum of the object is enough to counteract the downward pull of gravity. Now, the next question that's asked very frequently is what is a low Earth orbit, or LEO? A low Earth orbit is between 160 to 1,000 kilometers above the surface of the Earth, and typically the eccentricity is less than 0.25. The approximate velocity is about 7.8 kilometers per second, and it takes about 90 minutes to get around the Earth. And I think it's about 16 times per day for the International Space Station to orbit. That's how many times it happens per day. So when we get into orbits themselves, there is something about circularity, and this eccentricity is the value that defines that. Now, the eccentricity is how circular an orbit is, and if the eccentricity is too high, that means that the orbit is not very circular. It's very oblique, if you will. Now, if an orbit is circular, that means that the general velocity of the orbit is stable around the entirety of the parent object. However, if the orbit is very eccentric, so imagine we have an object here and we have an orbit here, what's going to happen over in this area is a very slow motion comparatively to this section right here. This will be the fastest at the periapsis and the slowest at the apoapsis. Excuse me. Well, why is that? Well, to be captured by an object, you have to be going a certain speed that counteracts the gravity of that object. And imagine we're an asteroid and we're approaching a planet and we end up going around just slow enough that it catches us and we get flung off. Well, if we slow down enough, we'll get caught again and get flung off again and again, and eventually our orbit will stabilize and peter out to either stick around or will eventually be slingshot into another solar system. Now, as I said before, low Earth orbit is a region of space between 160 kilometers to 1,000 kilometers above the Earth's surface. And this is where almost all of our satellites, communication, and otherwise reside. Of course, there is something also known as a geostationary orbit, which is a very specific distance away from a planet so that the satellite orbits at the exact same speed as the planet's rotation. So imagine you have New York City right here, and if the planet were to rotate and New York City was here, the satellite would be up here, meeting exactly above where New York City is. Now, this can be calculated in a number of various ways, but it is a complex mathematical beast, and we'll get into that another time if you're interested. Now, there is another factor here about gravity that we should get into. It's called the inverse square law. The inverse square law does not just apply to the intensity of light. It can also be applied to electricity and gravity. Big G, don't forget, is the gravitational constant. And remember, it is not the strongest force. It's hard to measure. So we want to find the gravity at y, or the surface, the intensity, gravity at the surface here, and we have a specific radius, or what we are going to say x, here, which we want to solve for. So our intensity will equal the mass times by the gravitational constant over radius squared, and this will equal little g, which is the gravitational pull of the object we are referencing, or the parent object. Now, when it comes to orbits in general, there are a number of things that can be used in various utilitarian ways. For example, we've all heard of the term slingshot effect. Now imagine you are on the Earth and you want to go to Mars way over here. You launch your object, but you're kind of low on fuel now that you've gotten up into space. Your delta V is running a bit low. So what you do is you accelerate your orbit to meet with the moon and use the gravitational pull to throw you off. The slingshot effect has been used by a wide variety and many, many missions by both NASA and various other space agencies around the world over the past 40, 50, 60 years. It's absolutely an incredible tool. Now, a few more things about orbits. You may have heard something called Lagrange points. What the heck are they? Well, what happens with gravity is that due to the inverse square law and a various number of other things, gravity at a distance becomes weaker, if you will. And there comes a time when these waves end up being counteracted by another object, which then creates a point of stability in which you can place an object and it will stay there. That is, in short, a Lagrange point. You will hear about Lagrange points especially when it comes to solar observatories, and as well as some of the other satellites that they have designed to observe the stars. Now, to achieve an orbit, you need to leave the planet's surface, typically in an equatorial region due to frameshift dragging and various other factors, as well as allowing the acceleration or the rotation of the Earth to help you in your ascent. And when you leave, you have to leave in an angular direction, because once you get up into space, you will then need to circularize your orbit as here with a low eccentricity. It's a lot easier to maneuver once you've had a little bit of time to take a break. Because as you orbit around an object, your window should be a few days out. If you plan to do it in the exact same day, you're probably going to have some hard times, especially if you miss it by a few seconds. Now, the launch profile of most objects that get into space is something more like this from the ground. If you have any questions, leave them in the comments below. We'd be happy to help you out, and we hope to see you next time. Don't forget to like, share, subscribe, and hit that bell for notifications.